Good morning. Perhaps you've been on a project with your Pico and thought, gee, the 23 digital pins and 3 analog pins just isn't enough. You want to control many more things. I've got just the chip for it for you. And we're going to go through the circuit and the software, the program, etc. to utilize it. Now, with the Pico, you've got 3 analog inputs. You've got 23 digital inputs or outputs. And with this chip we're going to discuss, it's called an MCP23017. It's a port expander chip. And there can be 8 of them on a board. Each one of those chips has 16 IOs, configured however you want, giving you 128 potential inputs and outputs. Or I should say inputs or outputs, not both. So that gives you a tremendous I/O capability on a little itty-bitty Pico. Using it, it's probably going to be a rather lengthy video to go over just the sheer volume of what we got to do with it. But using it, in truth, is quite simple. In this demo program that we're going to use, will certainly make it easy for you to understand. Now, the first thing we're going to do is look at the data sheet for this. We're using the I2C version of it, which is the MCP23017, and then the S version is the SPI, 23S17. That's the SPI version. As mentioned, it's got 16 bits or 16 pins, and each one is individually addressable, and it could either be an input or an output. More often than not, people just set up each of the 8-pin or 8-bit ports as either input or output to make life easy on themselves. These do come in a variety of packages. Obviously, I'm using a DIP package here on the breadboard. There are also interrupts, but I'm going to save that for another video if there is a request for it. A couple of things that we want to look at right away, maximum current out of VSS and maximum current into VDD. These are 2 important pins on the package, is 150 or 125 milliamps. This is absolute maximum. So you would look at this as the absolute most amount of current going in or out of the whole package. That's not a lot. If you take 150 divided by 16, you're at less than 10 milliamps maximum per pin. So keep that in mind. The maximum output current sunk, if you're providing voltage into the device through some object, or maximum current source providing voltage to a device, is 25 milliamps. But again, keep that in mind. That's maximum rating, and the maximum of the package certainly will restrict the maximum for any of the individual pins. We'll take a quick look at the chip layout. As mentioned, I'm using a DIP chip, and on the board, this the pin number 1 or the top surface here will be to the left on the breadboard. So here we've got one bank. It's called GPB 0 through 7. Over here, directly opposite of us, we got another bank of 8 pins, GPA 0 through 7. And just to keep in mind, it goes 0 to 7 in this direction, 0 to 7 going down on this side. So just keep that in mind. And then these other pins down here are going to establish the ID number for the I2C. And then over here, we're going to provide power and the I2C connections, or I2C, depending on how you want to say it. And that's really all we really need to garner off of the data sheet for right now. So we'll dive right into the fritzing diagram, which makes it very clear and easy to understand. But before I go into this, let's take a look over here on the actual breadboard. This is a large breadboard. I haven't used this in many, many years. I haven't done a project of this scale in a long time. In fact, there's a logic chip there. I believe that's a Schmidt trigger chip right here, and it might even be an inverting Schmidt trigger. So whatever I was doing on this board in the past, I was dealing with a signal that wasn't the way I wanted it, and this chip helps to clean it up and make it a nice signal. I'm sorry for the sidetrack there. Let's get back to our chip, or our circuit here. We've got our Pico. Down here, I've got a dip switch, a bank of 8 of those right here. And we're using that just to provide an input to the MCP 23017. And that's in the middle of the circuit board. And the output of that, I'm very lightly driving a series of LEDs. I don't want to leave them on for very long. 10 of them at 10 milliamps is 100 milliamps, and that would be pushing right at the far end of the capability of the whole package, the whole MCP 23017. You can do it momentarily, and it won't build up heat and destroy itself. And then those will go through a resistor, back around, and so forth. So this is the actual layout on the breadboard. It's very hard to discuss connections here because everything's kind of mushed together. So let's start out with our power distribution. We're running everything on 3.3 volts. So that's coming out here to this power rail, which will then come in to the MCP 23017 there. And then up here, we're running it to this power rail, which we're then bringing around to this point. And that'll be discussed a little bit later. Our ground is coming to one of the ground pins on the Pico, running that to this ground rail, which also continues up to this ground rail for a path for our LEDs to return current back. Coming down to this ground rail, we go from here into each of the dip switch positions, and of course we bring it up to the MCP 23017 chip. And that, we will look at those two right away here. That will be VDD is ground, VSS is our supply voltage. And that is, I'm sorry, VDD is supply, VSS is our ground in this case, or our 0 volt. We have no, oops. Hey. We have no connection on the one that's marked NC, no connection. And then we've got SCK and SDA, and then another no connection. SCK, SDA come back to here, and there is our SCL and our SDA. So those two signals continue back to here. These 3 ground wires are setting the channel number for the I2C interface, which is explained right here with A0, A1, and A2. You configure those in a certain combination to specify the address for it. And then the next wire, I believe, that would be this guy here. I don't think it's described on the chip, but on this line right here, we're pulling it high with 3.3 volts, and that is our reset. If we pull that high, it's staying in an active state. You drop it low, it's resetting the chip. These would be all configured in our example as inputs. These are all configured as outputs. Very straightforward there. Again, we got to watch our output current. Now we're going to come back to this point. We can see how this is ground to these switches, which go in to these inputs. So when we flip a switch on or off, we are switching that to ground, pulling that pin either high or low. On the output side, which we're going to configure this bank or this port as output, that'll go into, I'm showing a bar graph LED here, only because trying to get Fritzing to show 8 LEDs side by side like this is a nightmare, so I cheated and used a bar graph to represent our LEDs. But we are providing a voltage to it. We're sourcing the power to the LED, and then through these resistors at 330 ohms. Again, I'm trying to keep that current very low. And then the path of current is back to this ground rail, and then back to the Pico. And this is how you would wire these up. Now, if you've got multiple chips, you would configure its address differently here with these 3 ground wires, and you would have to continue these, your I2C wires, on into the next one and so forth. But you could replicate this circuit going to the left a total of 8 times for a grand total of 128 total I/O pins. Here in the program, I've provided plenty of commentary to get you familiar with what's going on in this example program. I won't go through the details here right now, other than you will notice that the demo is going to set up the A port, pins 0 through 7, as outputs, and then the inputs will be on port B, and those are pins 8 through 15. That'll help you keep track of what's going on. If it's 8 through 15, that's an input. If it's 0 through 7, that's an output, the way I'm going to configure it. Most importantly, you have to copy, download and copy. Here's the location for that library. You've got to have this library from a fella named Mike. I think his last name is on this link here. He did a brilliant job creating a library that makes it very easy for us to utilize this chip. In truth, 20, 30 years ago, I would have loved to sit and code that all out myself, but today I'm a firm believer in use the magic boxes that others create. They did us a huge favor, and we should pass thanks along to them. But this library is key. It is called MCP23017.py, and you just copy it into your Pico the same way you copy all programs in there. I want to mention that we want to be careful not to use too much current getting pulled from the Pico. The MCP23017 can be powered with an external power supply. You would just share the common ground wires between the Pico side of power and this side of power. You don't want to have 8 of these all drawing power from the Pico. It just can't provide that much. It can't source that much power. So be sure that if you're running multiples of these, or you're driving some fairly decent currents, kind of like what I'm doing here, power that separately. And then same is true with the MCP23017. Watch how much current you're either syncing or sourcing from that device. Now let's get into the code here. We're going to get from the machine library the pins and I2C interface. We're going to import Mike's library. We're going to import time. We're going to configure a couple of pins for the I2C interface. And we're going to configure the I2C interface. You can tell I really want to say I2C because that's what I used to call it many, many years ago. But it is truly I2C. It just makes me stumble. But anyhow, we're creating that object for our I2C interface, and we're just using the data from these 2 pins and setting the frequency at 400,000 hertz. Then we're going to create an object for our chip, our MCP chip, from Mike's library at this address, which is done with those 3 ground wires, A0, A1, A2. And the datasheet explains what that address would be, and then you would have to run a command here on the Pico to find out to verify that you've got it hooked up as well. Getting into the code, this is both a demo and example program. I'm going to set up a dwell that I might use as a constant further down. So it's just a time of 50 milliseconds. P is a variable that's going to be walking through a list of all the port pins, 0 through 15. And that's what's going on here. So if I want to turn all the LEDs on sequentially, and as we mentioned up here, I'm configuring that as an output. 0 through 7 are outputs. And actually just this action alone makes it an output, but we're going to go through those 0 through 7, which is what this statement's doing, one by one, and setting it to on. We'll sleep for the 50 milliseconds, and then go to the next one, and that'll animate them going on in sequence. And of course, we increment our counter, which is P in this case. Now we'll do the exact same thing, turning them off in reverse, or turning them off. So we'll go through the same exact while loop, going from 0 to 7. We'll set the output to 0, sleep a little bit, and increment our counter. Now I'm going to go to IP for a counter, and that'll equal 8, the base number for that pin. And just the sheer action of this is going to configure each of these pins as an input. So while IP is less than or equal to 15, so 8 through 15, we will set that as an input. And then we're going to also, after we set it as an input, turn on the internal pull-up resistor. Let me add that word in there, pull up. And then that way that signal's always high by default on our inputs. Pulled high right there. So that is, this little loop here is establishing those pins on that port as inputs, and they're pulled high. Now we're going to get into a while loop here. And this is going to be a kind of a meat and potatoes area of the program. It's a typical endless loop. IP is going to be reset back to 8, and we're going to have a new variable called port_s, and that's going to be equal to blank at the moment. We're going to go through with IP and scan it from 8 as IP, while IP less than or equal to 15. We're going to scan ports and pin 8 through 15. Now, if a pin is high, if one of these inputs is high, that means it is on. So we're going to calculate the pin number of the output. We will turn that output on, thus turning on the LED, and then we'll create a visual representation of that port state. And that'll make sense. We'll see that down here in a moment. So it'll be a binary code is what you're really going to see. 0 to 8, or I'm sorry, 8 to 15 being either a 0 or a 1, 8 bits equaling a byte. And then over here we've got the else-if condition. If that is not equal to 1, if the input is low, we will calculate our pin number for the output, and we will set that output to off, thus turning the LED off. And then finally, we will modify our string by adding a 0 to it. 0 meaning off, 1 meaning on. We'll increment our IP number, and go through all this again. So we'll do it 8 through 15, come back, 8 through 15, come back 8 through 15, and it just keeps doing that. And every time through, it'll print out what that port looks like, what our input states look like, and conversely, our output states. And then we're going to sleep a quarter of a second in between. So what's going to happen when I run this program, and it's all going to kind of happen, I am going to, first it'll go through, light these up, and then it'll take and make them dim. And I'm going to hold a gel or a filter over the LEDs so that they're a little more visible to you. And then over here at the dip switch, after it does that, it's just kind of sitting there, and it's in that loop. And what I'll do is I'll turn on or off some of these little switches on the dip switch. And you will see that when I switch that here, it's telling the MCP 2308, the Pico says, oh, you changed that? Now go out here and then turn on or off that output. So we'll go ahead and run it. And you just saw them go through. It went all off in sequence, back on. And now I'm going to turn off every other LED. Like that. And that is pretty darn cool. What this gives us, obviously, is, as it's configured, we've configured 8 inputs, and we've configured 8 outputs. The Pico reads the inputs as we want, and then we can control any outputs that we want. Here I just got the two tied together just to make it easily explainable that we've got inputs and we've got outputs. The Pico can read those inputs and do something on an output, or perhaps the Pico does something completely different. The important thing to remember with the MCP 2308 is it's not a driver. I'm showing that I'm running some LEDs here. Their current is very well limited, which, as you can tell by just this, the overhead view, those LEDs, they're reflecting almost as much light as they're generating from the overhead light. So you will need a buffer chip in between. And you'll want to see our other video on the ULN 2803 buffer chip that allows you to drive currents, but yet be switched with logic level outputs, because that's truly what this is. It's logic level input, logic level output. And logic level meaning 3 volts or 3.3 volts in our case, and a very small amount of current, less than 10 milliamps. But I believe that should be enough in the program to get you familiar with how to configure a port as an output, simply writing to it as an output, and then how to implicitly create a series of inputs by configuring them truly as an input, and then setting the pull-up resistor. Then finally, we can go ahead and utilize these inputs and outputs as we see fit in any combination to do anything at all that we want. All told, with about 150 IOs that could be on a Pico, that's a tremendous amount of control that's easily put in your hands. If you've never worked with an MCP 23017, I highly recommend you pick up a couple. I don't know their cost. It's been a while since I bought some. They can't be more than a few bucks each. And get a jumper and a nice big breadboard and do some experimenting so you can become familiar with them. They are a great go-to chip, and I've been using them for a very long time on many other different brands of microcontrollers over the years. So that'll wrap it up for this introduction to the MCP 23017. I hope you've enjoyed it. Hopefully you've gained a little insight into it, and now you've got a new value or appreciation for the value of that chip. That's it. Thanks for watching, and I look forward to seeing you in the next video.